Okay, we're going to go ahead and solve a complex circuit, okay? Similar to the last complex circuit we solved, the steps are to first find the equivalent resistance, then find the current, then find all the currents or voltages are the same and mark those down, and then solve for any of the unknowns that are left. Let's move that off to the side. Alright, so we've got this circuit up here. So the first thing we want to do is find the equivalent resistance, and in order to do that we need to simplify this circuit. So we're going to go ahead and look to see if we can find any pairs or triples of resistors that are either completely in series or completely in parallel. So if I start with resistor 1 and I compare it with resistor 2, I might say, hey, it looks like it might be in series, but it's not because there's a junction here. In series, you cannot have a junction between the two, okay? And they need to be connected with no junctions or batteries between them. So those two are not in series. Then I might say, okay, well maybe 2, 3, and 4, all those ones are in parallel. Well, to be in parallel, to be connected to the top and the bottom, or if it's oriented differently, the left and the right. Well, 2 and 3 are connected to the top. That's good. However, 2 and 3 also need to be connected to the bottom without any other resistors between them, and that's not the case. So 2 and 3 are not in parallel, and neither are 2 and 4 for the same reason. So you keep looking, and now maybe you come to the realization that 3 and 4 are in series. They are connected, and there is no junction between them. Okay, so we've got no junction, no battery between them, so we've got 2 that are in series. So we want to go ahead and find their equivalent resistance. So you need to recall back from the series circuits problems that when 2 resistors are in series, you find their equivalent resistance simply by adding them together. So the equivalent resistance for resistor 3 and 4 is equal to the resistance of resistor 3 plus the resistance of resistor 4. So we've got 3 is 2 plus 4 is 6. So the equivalent resistance for resistors 3 and 4 is 8 ohms. The next thing we're going to do is redraw our circuit. Okay? So we're just going to go down below here and redraw the circuit. So we still have our 12-volt battery. We didn't combine that with anything. And we still have our 3 ohm resistor. That was not combined with anything. And then we still have resistor 2. That's 4 ohms. So resistor 2, which is 4 ohms, is still there. And if we go over, here's where we combined. We combined 3 and 4 to be one resistor, and their equivalent resistance was 8 ohms. And there's our redrawn circuit. Okay, now I look at this circuit, it's still a complex circuit. Okay, that's still not completely series, not completely parallel. So I need to look at it in a little more detail. So here we go. We're looking at this one to decide, are there any resistors up here that are completely in series or completely in parallel? If I'm looking, I see that resistor that has the resistance of 4 ohms and the one that has the resistance of 8 ohms, they are connected at both the top and the bottom. Therefore, they are in parallel, so I can connect them. So I need to find the equivalent resistance for my 4 and 8 ohm resistors. Well, to find the equivalent resistance when they are in parallel, we have to add with the reciprocals. So 1 over the equivalent resistance for the 4 ohm and the 8 ohm is equal to 1 over 4 plus 1 over 8. Now remember, when you're adding fractions, you need a common denominator. So the common denominator here is going to be 8. So I have 2 over 8 plus 3 over, got ahead of myself, plus 1 over 8 gets me 3 over 8. So 1 over the equivalent resistance for resistors 4 and 8 is equal to 3 over 8. I'm not done. It's not 3/8. Okay, I have to solve this. So you can cross multiply, or since there's a 1 on top, we're basically just flipping it over. So we have 8/3. We can leave it as a fraction or we can make it a decimal. If we make it a decimal, we are going to round to 3 decimal places. So I'm going to get 2 5.667. All right, when we're done, we redraw it again, okay? The battery was not combined with anything, so the voltage of the battery is still 12 volts. The resistor up here was not combined with anything, so it still has a resistance of 3 ohms. These two were combined, so I'm going to draw them as one resistor. And I'm going to use their equivalent resistance, which was 2.667 ohms. Now we've got a simple circuit here, so we can go ahead and solve. So when I solve the simple circuit, I'm going to first ask what type is it, series or parallel. This is a series circuit. What stays the same? That'll be current. And what do we need to do first? Find the resistance at the battery, the equivalent resistance overall. So it's a series circuit, so we simply add them. So 3 plus 2.667 is 5.667. If you want to keep it as a fraction, you could. You'd get 17/3. The next step is, well, we know the current stays the same everywhere, but we don't know what it is. The only place I have enough information to find the current is right here at the battery. So I'm going to go over here and use Ohm's law, V equals IR. So 12 is equal to the current, which is what we don't know, times the resistance of the battery as well, which is 5.667. Solve this by dividing by 5.667 on both sides, and we get the current is 2.118 amps. Again, I'm rounding to 3 decimal places here. You could also leave it in fractional form and you get 36/17, but I'm going to go ahead and just do decimal. So I've got 2.118 amps. And now, this is a series circuit. Current is the same everywhere. So the current at the first resistor is 2.118 amps. And the current, the second resistor, is 2.118 amps. Last step, find the missing components, missing pieces. So I need a voltage drop at each of these resistors. Well, again, we're going to use Ohm's law. Okay? So V is equal to 2.118 times 3. So the voltage drop here is 6.354 volts. Down here, we're going to take the voltage drop is equal to 2.118 times 2.667, and we're going to get that the voltage drop is 5.649 volts. If you're following along so far, great. The next part is where some students start to get a little confused. Okay? So, we're going to go from this picture to that picture. If the items stay the same, if they don't become 2 or 3 in other cases, then we just write everything the same. So the battery is the battery the whole time. It doesn't get combined with any other batteries. So everything stays the same. So the current is still 2.118 amps, and the resistance of the battery is still 5.667 ohms. This resistor didn't get separated into 2. Still the same thing. So everything stays the same. So the voltage is still 6.354 volts. And the current is still 2.118 amps. Here's where we have a difference. This one resistor is broken into 2 because we combined it to 1 before. Okay? These two are in parallel. When 2 resistors are in parallel, what stays the same? Voltage is the same. What that means is I take the voltage from where they're combined and I use it for the voltage where they are not combined. So it's 5.649 volts for both. And now I need to solve for the current. So let's solve for the current using Ohm's law, V equals IR. the resistor of 4. So 5.649 is equal to the current times the resistance of 4. Divide both sides by 4, you get a current of 1.412 amps. Okay, we need to find the current here as well. So again, Ohm's law, 5.649, the voltage is equal to the current times the resistance, this time 8. So divide by 8, we get a current of 0.706 amps. All right. Now we've got everything for our intermediate one. So we're ready to go up to the next one. Now remember, you can check these using Kirchhoff's voltage law and Kirchhoff's current law. So here, the currents need to add up to be this. So if you type in your calculator 1.412 plus 0.706, you're going to get 2.118. Okay, so you can use that to check your work as you're going. Now we need to go from the intermediate step back to the first step. Well, things to take note of. The battery, still one battery, didn't get combined with any other ones, so it stays the same. So I have the current 2.118 amps, and I have the resistance for the entire circuit still at 5.667 ohms. This first resistor, still just one, so everything stays the same. So the voltage here is still 6.354. And the current is still 2.118 amps. This resistor is the same. It's 1 and 1. So the voltage is still 5.649 volts, and the current is still 1 and 412 thousandths amps. Here is where our difference is. This one resistor becomes 2. Why? We combined it to make it 1 when we are going down. So now we need to say, what are these two in? They are in series. In series, the current is the same. That means I come here and I take the current and I write it for both of these. So the current is 706 thousandths amps. The only thing missing from our original circuit now is the voltage drops at each of these resistors. So we need to find the voltage drop at each resistor, and we do that using Ohm's law. So V equals IR, so voltage is equal to 706 thousandths times 2 ohms. So the voltage drop here is 1 and 412 thousandths volts. And then the other one down below, we have the voltage drop there is equal to 706 thousandths times 6 ohms. So the voltage drop there is 4 and 236 thousandths amps. Sorry, voltage drop measured in volts. Okay, and now we have solved the complex circuit.